Hi everyone. What we have here is an electromechanics problem. The question is asking if we have two particles of the same charge and they're traveling towards each other, they're same polarity, and they're traveling towards each other from infinitely far apart at a given velocity v, how close together will they get before they turn around? And I mentioned this in an earlier video. It was a little confusing for some people. We talked about it today in the help session. But I'm going to reintroduce this concept that potential energy, the change in the potential energy is equal to the kinetic energy, or the negative change in the kinetic energy, depending on what framework you want to think about it in. Basically, the change in one is equal to the change in the other. So in this case, what we have on the upswing is just kinetic energy. And when we hit this point right here, X marks the spot, we have 0 kinetic energy and 100% potential energy, and then they fling each other back away from each other. So when we're calculating this out, we start with our formula for kinetic energy, and we're given m and v. We only need to calculate it for one particle because in a general framework for physics, this particle is standing still relative to this one's motion, or vice versa. So that velocity is them relative to each other. So we only need to use the velocity of one as if they're standing still. So we get 1/2 mv squared. And then the formula for potential energy, which I believe we've gone over before, is equal to k q1 q2 over r. And in this case, q1 q2 is just q squared because q is given. So let's plug in some numbers. We get 1/2 times 7.9 times 10 to the negative fifth. And then v is equal to 9.694 times 10 to the third, so 9.694 times 10 to the third squared, and that's equal to k q squared over r. Well, we want to solve for r, so I'm going to erase this real quick and just write out the algebra for r. So what we have here is 1/2 mv squared equals k q over r, or is equal to k q squared over r, because they have the same charge. So then we get that k q q2 over mv squared is equal to r. And that's just by flipping these. So we get kqq times 2 over mv squared is equal to r. And we can just plug that in and get r. With these given numbers, it would be 9 times 10 to the 9 times negative 940 times 10 to the negative 6 squared times 2 over, and then in our case it would be mv squared, so 7.9 times 10 to the negative fifth times 9694 squared. And this is equal to r, which is the value we're looking for. Okay, so the second question is actually nearly identical to the first question, but without the turnaround. So let's think about it from, we've reached the point we were going to. We have the same polarity, they're moving away from each other now. We can fix this one the same as we did in the last one. So we start with k qq over r, and we're given k qq and r, and we want to end with 1/2 mv squared. So solving for v is our goal, because at infinity, will have 0 potential energy because R is infinity. And at infinity, that means that this has to be equal to the initial potential energy. So at infinity, we've run out of potential and we've gained all of it as kinetic. We can think about it as for each line we cross, for each equipotential line we cross, we gain some amount of kinetic energy and lose some amount of potential energy. So let's just do the algebra and work out what we get for V. We get kq squared over r equals 1/2 mv squared. So then 2kq squared over r equals mv squared. So 2kq squared over rm is equal to v. So then 2kq squared over rm square root is equal to v. And we're done. So I'll circle this and then we will circle back around. Okay. So, if you have any questions about that, feel free to email me. And when we're working on problems like this, the key thing to take away is that the change in the potential energy is equal to the negative change in kinetic energy. As we travel along these potential lines, we're losing some potential energy because this is a negative change in potential energy, this is a negative change in potential energy, which means that this is a positive change in kinetic energy. Cool.